The new section is entitled Expectation of Sums of Random Variables. Expectation of sums of random variables. Okay. So let's start off with two theorems. One is discrete, and the other one is the counterpart for continuous. If x and y have a joint probability mass function p of xy, then the expected value, and we're not going to prove these, the expected value of g of xy, some other function of x and y, is the summation of y times the summation of x of g of xy times the joint probability mass function p of xy. And these are all theorems. That's theorem number 1. Number 2. If x and y have a joint probability density function f of xy, then e of g of xy, is going to be the double integral. Instead of summations, we have double integral. And both x and y can be any value, and you multiply this by g of xy times the PDF f of xy dx dy. Those are two main theorems when you talk about the sums of random variables. Okay. You have a lot of fun with this stuff. Suppose you have a road, and the length of the road is L. L miles, L units. Okay? And there's a car accident on this road. Right here is X, and it's the location of the car accident. And at some distance away, you have an ambulance. Okay, y represents where on the road the ambulance is. Now, maybe this is 0 and this is L. It starts at 0, it finishes at L, hence the length is L. And x and y represent where, x represents where the car accident occurred. Say if x is 2, that means if the units are in feet, 0 feet, L feet. Well, if x is 2, that means it happened 2 feet from the start of the road. And if y is 11, well, then it happened 11 feet from the start of the road. Now, since x and y are random, maybe it's not random. I was going to say where you have a car accident on this road is random. That is uniformly distributed. But, maybe somewhere on the road there's an intersection and you have a higher chance of having an accident there. And, maybe maybe on this road, you only have a few people living here, and maybe more people live in the middle, and maybe you have an awful lot more people living on the end. So what point does this make? Well, the ambulance has more of a tendency to probably be at the end of the road than it is at the beginning of the road. Why? You have more people, you have more need for an ambulance. So what I was about to say was incorrect. That it is obviously uniform. X and Y are obviously uniformly continuous. But let's make this statement. Suppose X and Y are uniformly distributed. They're uniformly distributed. That is, the probability of being anywhere on the road or being in some interval on the road is just as likely as being on another interval of the same size. Okay. Now, we're also going to assume X and Y are independent. That is, Y can be anywhere on the road independent of where X has the accident. Knowing where X had the accident will not influence you on knowing where Y can be. Okay, that's what uniformly distributed kind of means anyways, when you say X and Y are both uniformly distributed. Okay, so X and Y are independent. That is, wherever Y happens to be is not going to influence where X has the accident. Okay? I'm kind of saying that it was one should kind of know that they're independent, but once again, there's a slight chance if Y is over here, it's a vehicle. It's one more chance for where an X goes down the road to have an accident. Okay? If Y happened to be over here instead, there's a bigger chance than a moment ago that X has an accident right here. That the car accident happens right there. Why? Because there's another vehicle. If there's no vehicle, you're probably not going to have an accident. We assume you don't hit the wall. Okay, so yeah, you do have to say they're independent. But I would assume the probability would change ever so slightly. Putting another car on the road, the chances are you probably won't have an accident. But if there's just one more car on the road, it's not going to up your chances of having an accident. Okay, so nonetheless, we're going to assume X and Y are independent. All right. So now, we want to calculate, find the expected value of the difference in the distance. Now, since it's distance, we're talking absolute value. It is how far, what do you expect the distance to be between X and Y? And what you might want to do is, based on this information, you might want to decide how many ambulances you should put out. Okay, what is the expected distance between X and Y? Okay. Well, what is f of xy? That is, what is the probability that x is little x and y is little y? And since we're assuming independence, this is the probability that x is x times the probability that y is y. Now, since it's uniformly continuous, both of these functions are constant. It's 1 over L. They're both 1 over L. If this is L, remember the height's going to be the same because it's uniformly distributed. And since this area must be 1, and it's the area of a rectangle, this must be 1 over L, because 1 over L times L is, in fact, 1. So it turns out that it's 1 over L squared. 1 over L times 1 over L is 1 over L squared. I said it turns out to be 1 over L squared, and that's this. That's that. F of xy is 1 over L squared. Okay. So now we need to be a little bit clever. So now E of the absolute value of x given y. Well, I guess I should talk about this. What is x minus y in absolute value? What does that equal? Let me get this out of my way, please. Well, sometimes you just get x minus y, and sometimes you get negative x minus y for the record, which is y minus x. Well, what I wrote down first is exactly what I put in there, and that's when it's positive or 0. Bringing the y over, but that's when x is bigger than y. And when do you get the negative of that? And that's when what you're taking the absolute value of is less than 0. Bringing the y over, x is less than y. Okay. So now that we understand better what we are taking E of, namely the absolute value of x minus y, we can continue. This is equal to the integral, the double integral. The x and y both go from 0 to L. X can only be, x is on the road. It can only be somewhere between 0 and L. Same thing for y. And it's this function times f of xy, which was 1 over L squared. And this is dx times dy. Okay. The constant 1 over x squared we can put in the front. Now I want that bottom equation to remain. So let me erase this. In fact, let me put it on the top. I wanted it to remain so it's in front of me. So E of the absolute value of x minus y is equal to the double integral, both going from 0 to L. The 1 over L squared can come in front. And we have the absolute value of x minus y dx dy. Okay. So we're going to put most of our energy right now to figure this out. What is that integral? So it's 1 over L, oops, not L sub 2. It's 1 over L squared times the integral from 0 to L. I'll work on this in a moment, times dy. Times dy. Actually, let me put a bracket here. Now, nope, that statement isn't what I wanted. I'll put the bracket here. Just where I put the curly bracket. Okay, so we're going from 0 to L. Now, we're going from 0 to L. Now, if y is over here, and x, well, let me do this. If y is where I said, and now, so for either x is before y or x is after y. Those are the two cases. If x is between 0 and y, that is, x is less than y. But listen to the first thing I said. X is between 0 and y. Then x is less than y. So the absolute value of x minus y will be y minus x dy plus dx. At the very end, we'll do dy dx. Plus, now, x is going to go between y and L. X will go between y and L. And if x is anywhere here, x is bigger than y. And the absolute value of x minus y. If x is bigger, it's just going to be x minus y. And we're integrating that with respect to x. So you have to be mathematically mature enough and know exactly what the absolute value of x means. Sometimes, the absolute value of x minus y. Sometimes it's x minus y. Other times it's negative that. Okay, so now we are in very good shape because the probability is over. We just have to integrate. So it is 1 over L squared times the integral 0 to L of what's inside the big brackets dy. Well, the first integral, remember, with respect to x, the integral of y dx is yx minus the integral of x is x squared over 2. And this goes from 0 to y. Plus, with respect to x, the integral of x is x squared over 2 minus the integral of y is y times x. And that goes from y to L. So it is 1 over L squared times the integral of L of, remember, these are x values. You plug in y, you get y times y, or y squared, minus y squared over 2, minus, and when you plug in 0 for x, you get 0. So I'm not going to bother taking away the 0. Plus this piece. First you plug in L, just like y, you get L squared over 2 minus y times L. Minus, now you plug y in. You get y squared over 2 minus y squared. Okay. Times dy. Now, it turns out that, okay, so you have 1 over L squared. We have some stuff that combines. Y squared minus a negative y squared is 2y squared. And if you take away half of y squared, and then you take away another half of y squared, well, you took away y squared dy. This is 1 over L squared times the integral where y goes from 0 to L. 2y squared minus y squared is 1y squared dy. So you have 1 over L squared times y cubed over 3, and y goes from 0 to L. And I will continue at the very top. this all was equal to the expected value of the absolute value of x minus y. Now, if you plug in the y value, the 1 over L squared I'll factor out. You plug in the y value, which is L, you get L cubed over 3. And if you plug in 0, you get 0. 2 of the L's in the bottom, kill off 2 of the L's on the top, leaving just 1 L on top. 1 times L over 3. The probability, or the expected value of the distance between the car accident and the ambulance will be L divided by 3. It will be L divided by 3, a third of the length. That was a great problem. L divided by 3. You had to be very clever how you figured out what x minus y was going to be. The limits, that is. You have to have a strong command of the absolute value of x function. Okay. Try something else. Suppose x and y, well, that's not true. Suppose the expected value of x and the expected value of y are finite. They are not infinity. Are finite, and x and y are continuous. X and y are continuous. If we let that g function be x plus y, what is e of g of x? That is, what is e of x plus y? Well, by definition, or by that theorem, it's the double integral from negative infinity to infinity for both limits. G of x times the PDF times dx dy. Okay. And now we need to be clever at how we break this up. The first thing I would do is just basic distribution. I'll distribute. You have x times f of xy, and first I'm going to do the dx. Okay, you get x times f of xy plus y times f of xy. Dx dy. Okay. In fact, what I can say is this. Is x times f of xy dx dy plus this integral, the integral of y f of xy dx dy. And the limits, all right. All right. Let's say it this way. Okay. Now, what I can do is I don't have room to write the limits. They're both negative infinity to infinity. The first one, the first term, I'm really not going to change. I might put brackets around it like this, but It's not going to change. Actually, it is going to change. I'm sorry. I can change the order of the limits since they're both going from negative infinity to infinity, plus the second term, this is y, f of xy times dx times dy. Alright. Let's go to the top and finish this up. Actually, let's try to do it in this space. Now, to save a little space, I'm back to the very, very bottom. This x I can put in front. Actually, let me write it. It's the integral of x times the integral of f of xy dy times dx, plus the integral, this time in this second integral, that doesn't really look like a bracket. The second integral, I can pull a y out in front, or the second term, I can pull a y out in front, because it has nothing to do with x's. Alright, so it's the integral of x times this, dx. But what's in that bracket? The integral from negative infinity to infinity of f of xy dy, y is changing. Well, that's f sub x. That's f sub x dx, plus the integral of y times what's in here. Well, that integral from negative infinity to infinity is f sub y dy. Okay. And here's where it comes together. The integral of x times the PDF with respect to x, that's e of x. Remember, e of x is the integral of x times the probability. Here's the x, there's the probability, times dx. This second integral, it does say plus, this second integral is just e of y. The second integral is just e of y. Okay. This is major. This is major. Let's write down what we just said. Let's write down exactly what we just said. We just said that if e of x and e of y are finite, and x and y are continuous, then e of x plus y is e of x plus e of y. If e of x and e of y are finite, and x and y are continuous, then we have this. And I know we do. We just proved it. Okay. So now, what if we have e of x1 plus x2 plus x3 up to xn, and I'm telling you that each e of x1 and e of x2 and e of x3, etc., are finite, and any two are continuous. That means any three are continuous, any four. Well, what you can do is you can bracket it up like that. So now and this is just one random variable. So now we are adding two random variables. They're both continuous, and E of both of these are finite. So now we have E of the first plus E of the second. x2 plus x3. Let me write x4 all the way up to the last one. So here's E of x1. So let me write that. E of x1 plus. I'm going to bracket it this way. Here is one random variable. Here is the second one. E of each of them are finite, and both of the random variables, the ones the arrows are pointing to, are continuous. So I can say it's E of the first one, E of x2, plus E of the second one, x3 all the way up to xn. And this is not a rigorous induction proof. But if we do this, I don't know, n times or n minus 1 times, we do this enough times, we have this. Again, the title of this section was their expected values of sums of random variables. Expectation of sums of random variables. Well, here's the sum of random variables, and we're talking about the expected value of them. If the expected value of any one of the if the expected values of all the random variables are finite and they're all continuous, then you have this theorem where you can break them up. E of x1 plus E of x1 plus x2 is E of x1 plus E of x2. And then you can do wonderful things with this. It's just endless what you can do. For example, you can do the next problem. You can talk about the expectation of a binomial random variable. And you might say, well, didn't we find the expected value of a random variable? It was n times p. Well, yeah. But we're going to see it differently now. Let x be a binomial random variables. And binomial random variables come with parameters. With parameters n and p. N is a number of trials. P is a probability of success. Okay, so x counts the number of successes. Now, we're going to define another set of random variables, x sub I. Now, x sub I is going to count the success of the ice trial. We're going to perform this binomial experiment, say toss in the coin 50 times. So x sub 2 is going to be whether or not you got a head or a tail. Let x count the number of heads. Success is, say, heads. Well, it's going to be 1 if the ice trial is a success. The x sub 15 will be 1 if the 15th toss of the coin ended up being a head. It's going to be 0 otherwise. If you don't have success of a multiple choice test, each problem has 5 choices. Okay, did you get the 7th one right? Well, then we're going to put a 1 for x sub 7. You got the 7th problem wrong? we're going to put a 0. Okay. Now, E of xi is the summation of all over x of x times p. Okay, well, what are the values that, well, maybe the summation of xi. Well, what can x be? It can be 1 or 0. So if x is 1, you get 1 times the probability of success, which we're told is p, plus the other value that x can be is 0, and you multiply that. When does that happen? When you don't have success. That is, you have failure. The probability of failure is q. But that doesn't even matter because this is going to be 0 anyways. This is 0. This is p. You add them up, you get p. The probability that on the ith trial you have success is p, which made sense. Because it's binomial, it doesn't, they're independent trials. Alright. So now, E of x is, well, what is x? X counts the number of successes. Well, if you add up x1 and x2 all the way up to xn, remember, it's either 0 or 1. And it's 1 if you had a success. It's 0 or 1. The last one is either a 0 or 1. So yes, let me erase the e for a moment. Yes, x does equal x1 plus x2 plus x3 up to xn. So, since they're equal, their expected values are equal. Now, e of x1 and e of x2 and e of x3 are finite. The most they can ever equal is 1, and the least is 0. That's finite. So, each of these are finite. And the other one was they are continuous. And yes, they're continuous. So, this is equal to e of x1 plus e of x2, etc., all the way up to e of xn. But I know that each one of them is p. P plus p plus p plus p, and finally plus p. We're adding p to itself n times. You add p to itself n times, you get np. Exactly what it was supposed to be. So now we have this new way of calculating the expected value, expectation of a binomial random variable. It's just n times p. Now, here's a nice problem. Suppose you have an urn. And the urn has capital N marbles. M are white, and that's all you know. You don't know anything else. You know the rest are non-white. M equals the number of white marbles. You have a big urn. N equals big N is the total of marbles. Okay. You want to choose N, little n. You want to choose N marbles. And you want to know the expected value of the white balls. Find the number of expected white balls. You choose N marbles, How many do you expect to be white? How many do you expect to be white? Okay. So there's a number of ways of doing this. I know of at least 3. You can probably think of others. But the number of expected white balls. Let's do it like we did the last one. Let xi represent, well, xi is the number, okay. Alright, the xi is equal to 1 if the ice marble is in fact white, and 0 if it is not white otherwise. So if x represents the random variable that counts the number of white balls from the n. You choose n marbles. If 7 of them are white, well then x is 7. If 7 of them are white, then x is 7. If you choose n marbles and 14 are white, then x is 14. Well, x is going to equal x sub 1 plus x sub 2 plus x sub 3. Well, we're only picking n marbles. So it goes up to x sub n. And these quantities are either 0 or 1. That is, they're finite. And so is capital X finite. And they're also continuous. Okay. So now, I guess we need to know what E of xi is. I mean, but basically, I'm going to say E of x is equal to E of the right side, which is, I took E of the left side. Now I am taking E of the right side. And because of the structure of these x sub i's, I can take E equals E of x1 plus E of x2. And I stated why, because E of xi is always finite, and the xi's are continuous. So I can kind of distribute the E. Not always, but under certain conditions. And these conditions have been stated a few times now, and have been satisfied in this case. Okay. Now, if I knew what each of these were, I would simply add them up. Well, what is E of xi? What is the... Well, it's the summation of x times p. It's the summation of x times p. Well, x is either 0 or 1. I have to multiply the x's by their probabilities. Well, to get 1, if x is 1, that means the ice marble is white. Well, there are capital N marbles, and there's only one of them in the ice trial that's white. And the probability you get 0, well, there's n minus, that means you didn't get a white ball. There's n minus 1 balls that are non-white out of n. The bottom line is this is going to be 0, and 1 times 1 over n is 1 over n. Actually, that's not true. That's absolutely not true. I'm saying is complete nonsense. The probability that their ice ball is white, well, excuse me, there's m white balls out of n. The probability the first one is white is going to be m out of n. And the probability of the second one is white has the same chances as the first. And the probability of the third one being white has the same chance as the first two. Now, need to be clear. I'm not saying the probability of the third one is white is m over n, given what we saw for the first two. Okay, before we even put our hand into this urn, I'm asking you, what's the probability, suppose there's 20 marbles, what's the probability that the 15th one be white? Well, whatever that answer is, it's the same as the 11th marble being white. It's the same as you picking the third marble and it being white. Okay, they're all m over n. And 1 times that is m over n. And when you add 0, well, so if you want the probability of not being white, m minus 1 are not white over n. In any case, you get m over n. So this here is little m over big N. This here is little m over big N, and so on. So what we're doing is we're adding up n over n many times. How many times? The first time, oh, look at that subscript. The second time, oh, look at that subscript. The last time is n. The answer is the expected value will be m times n over the total. So if you have 7 marbles and there's 15 and you want to choose 3, the answer will be multiply 7 number of marbles times how many you're choosing, 21, and divide it by the total number of marbles, which is 15. So the probability will be 21 over 15, which is what, 7/3, which is 2 1/3. Well, that makes no sense. Divide by 3, you get 7/5, which is 1 2/5. If there were 15 marbles in all, and you want to choose 3 of them, and 7 of them are white, about half of them are white, a little bit less than half, keep in mind this 2/5 is 0.4, 1.4. Little bit less than half are white, and you're going to choose 3 of them. So you should get a little bit less than half for 3, which is 1 1/2. And 1.4 really is a little bit less than 1 1/2. And this was another type of problem you were able to solve expectations for using the sums of random variables. But remember, the random variables, the expected value of these random variables had to be continuous, and the expected values had to be finite, and they all had to be continuous. Okay, that completes this section.